Welcome to TalkTensors, the show where we really unpack the latest research in machine learning.
Great to be here.
So today we're diving into a paper that caught my eye. It's called Combinatorial Optimization for All, using LLMs to aid non-experts in improving optimization algorithms.
Yeah, that's a mouthful, but the core idea is pretty compelling.
Totally. I mean, if you've ever looked at optimization problems, finding the best route, scheduling stuff, the number of algorithms out there is just, well, huge.
It's overwhelming, definitely, and super complex.
Right. And this paper asks something really neat. Can these big, large language models, the AI behind things like ChatGPT, actually help make these optimization methods better?
And critically, can they help people who aren't deep optimization experts? That's the key part.
Exactly. Can an LLM take an algorithm that already exists and sort of tune it up without the user needing a PhD in operations research?
So they tested this by focusing on a real classic, the Traveling Salesman Problem, or TSP.
Yeah, the TSP. And they took 10 different established algorithms for it as their starting point. Let's dig into what they actually did and found.
Sounds good. So the paper really sets the stage by talking about this vast landscape of optimization algorithms. It's a field with decades of history.
Right. People have been cooking up ways to solve these hard problems for ages.
But actually improving these algorithms, that usually takes some serious expertise. It's a high barrier to entry. So this paper is like, okay, what if LLMs could lower that barrier? Make it easier to enhance these tools.
Yeah, they make a point of saying they're not focused on generating algorithms from scratch, which others have looked at.
Right. Their focus is more practical, maybe.
Yeah.
Enhancing what we already have, which could be more immediately useful for a lot of people.
Okay, so maybe let's put that in a bit of historical context. Combinatorial optimization, the TSP specifically.
Yeah.
Goes way back, doesn't it?
Oh, yeah. Almost a century in different forms. And trying to solve it better has really pushed algorithm development forward. You've got everything from early exact methods to, modern meta-heuristics.
And traditionally, like you said, tweaking those required deep knowledge. You couldn't just jump in.
Not easily, no. You needed to understand the math, the logic, the trade-offs. It's involved.
So this paper kind of lands at this moment where LLMs are getting really good at understanding and even writing code.
Exactly. So the researchers are basically asking, can we point that coding ability towards improving these complex optimization algorithms? Could it open the field up?
Democratize it a bit, maybe?
That's the potential, yeah. It's like having an AI assistant that gets optimization concepts and can suggest smart changes, even if you don't know all the theory yourself.
And using the TSP makes sense because it's so well studied. There's lots of existing code and knowledge for the LLMs to potentially tap into.
Precisely. It's a perfect test bed.
So tell us about the 10 algorithms they picked. You mentioned they were diverse.
Yeah, and that's important. They didn't just pick variations on one theme. They grabbed algorithms from different families.
Okay.
So you've got meta-heuristics, things like ant colony optimization, genetic algorithms, simulated annealing, taboo search, those smart search methods.
Ones that kind of explore and learn.
Yeah, often using randomness and learning principles. Then they included reinforcement learning ones, Q-learning and SARSA.
Where an agent learns by trial and error.
And they also had deterministic heuristics like Christophaides and convex Hull. These follow fixed rules. They're usually fast, but maybe not optimal.
Predictable, but maybe not the absolute best answer.
Right. And finally, they even included an exact algorithm, branch and bound.
The one that guarantees the best solution, but can take forever.
That's the one. Takes a long time on bigger problems. So this variety lets them see if LLMs are good at improving different kinds of logic.
And they used a standard library for the base code.
Yeah, the Combinatorial Python library. So they were starting from reliable, community-used implementations. Good baseline.
Smart. Okay, so the core of it.
Yeah.
How did they actually get the LLMs to do the improving? What was the method?
Right, the methodology. They built a prompt template. Think of it like a detailed instruction sheet for the LLM.
Okay.
It basically said, here's the code for algorithm X. Your job is to improve it, focus on getting better quality solutions and making it converge faster.
So clear goals.
Very clear. And it wasn't just a one-shot thing. They had this iterative process.
Iterative. How so?
Well, if the LLM spat out code that didn't run or had obvious logical flaws, they'd tell it, hey, this is broken, try again. they'd provide feedback.
Like debugging with the LLM.
Kind of, yeah, guiding it towards a working, improved solution.
That makes sense. What about the prompt itself? Anything special there?
Yeah, they used a couple of neat techniques. Role prompting, telling the LLM to act like an optimization expert.
Giving it a persona.
Exactly. And in context learning, they fed the entire original algorithm code into the prompt.
So it had the full picture.
Right. Lots of context. The prompt also dynamically included the algorithm's name, its function signature, stuff like that to keep it focused.
And they asked for documentation too.
They specifically asked the LLMs to write detailed doc strings explaining what improvements they made and why, even referencing known techniques if possible.
Oh, that's crucial. You need to understand the changes, not just get new code.
Transparency, yeah. Vital.
Okay, so they've got this process. How do they evaluate if it actually worked?
Rigorously. They picked 5 top LLMs, Claude, Gemini, Llama, and then 2 others called O1 and R1, accessed via the Open Router API.
So 5 LLMs trying to improve 10 algorithms,
But
50 new versions.
50 LLM-generated codes, yeah. And because many of these algorithms have random elements and parameters.
Right, the meta heuristics and RL ones.
They needed tuning. You can't just compare them with default settings. So they used a tool called iRace to automatically fine-tune the parameters for most of them.
That's good practice. Ensures a fair comparison.
Definitely. They tuned 42 out of the 50 generated codes, plus the originals where needed. Then they benchmarked everything on 10 standard TSP instances from TSP-lib, ranging in size.
And what did they measure?
Primarily, the quality of the best solution found within a time limit. For branch and bound, though, they focused on runtime to find the optimal solution, but on smaller, specially generated instances since it's slow.
Makes sense. And they ran the random ones multiple times.
Yep. 30 independent runs for the stochastic algorithms to get reliable average performance, controlling for randomness. Deterministic ones just needed 1 run, obviously.
Okay, solid setup. So the million-dollar question, did it work? Did the LLMs improve the algorithms?
Well, the results were pretty encouraging, actually. They saw improvements across different categories. It wasn't a magic bullet for everything, but yeah, there were definite wins.
Like what? Give us some highlights.
Okay, so for meta-heuristics, with ant colony optimization, several LLMs, including Gemini and this open model R1, often beat the baseline. For genetic algorithms, R1 really seemed to shine. Adaptive large neighborhood search saw good results from Claude and Gemini.
So different LLMs excelling at different things.
It seemed that way. R1 also did well improving taboo search and simulated annealing.
Okay. What about reinforcement learning?
Q-learning was tougher. The original held up well. But for SARSA, this O1 model showed pretty consistent gains.
And the deterministic ones. Christofeeds. Convex hull.
O1 and R1 managed to improve Christofeeds, especially on bigger problems. And Gemini looked best for enhancing the convex hull algorithm.
Wow, even the exact branch and bound, could they speed that up?
Yeah, O1 and R1 generated versions that achieved faster runtimes to find the optimal solution on those smaller test cases.
That's quite impressive across the board then. It really suggests LLMs can make meaningful improvements to these diverse algorithm types.
It does. It's not just code generation. It seems they can analyze and apply optimization principles. And the fact that different LLMs had different strengths is also interesting.
Yeah, maybe related to their training data or architecture. And you mentioned R1, an open model, doing well.
Yeah, R1 showed up strongly several times, which is great news for accessibility and the open source community.
Cool. Do they give any specific examples of how the LLMs improve the code? Like what kind of changes were they making?
They did. They included 4 case studies, which are really insightful.
Okay, let's hear about those.
So take the genetic algorithm improved by R1. The LLM didn't just tweak parameters, it added some sophisticated stuff, like using a nearest neighbor heuristic to generate a better initial population. That gives the GA a head start.
Ah, smart. A common trick. But the LLM identified and used it.
Right. It also implemented adaptive operator selection, smartly choosing between crossover and mutation during the run, and even added a local search step at the end to polish the solutions.
Wow, okay, those are non-trivial improvements, things an expert might do.
Exactly. It shows the LLM isn't just making surface-level changes, it's integrating established, effective techniques.
What else? You mentioned simulated annealing.
Yeah, the R1 enhanced version for SA, it implemented an adaptive cooling schedule.
So not just a fixed cooling rate, but one that changes based on progress.
Precisely. And again, it used that nearest neighbor heuristic for the initial solution guess. Getting a good start seems to be a common theme.
Makes sense. And the RL one, SARSA.
That was improved by the O1 model. The key change there was introducing Boltzmann exploration.
Boltzmann exploration.
Yeah.
It's about balancing, exploring new actions versus exploiting known good ones, right?
Exactly. It's a more nuanced way to manage that exploitation trade-off than simpler methods. And the researchers noted the implementation looked like it might have been inspired by a specific research paper.
Whoa. So the LLM might be effectively reading and applying knowledge from literature.
It certainly suggests a deep knowledge base, potentially including academic sources. It's quite remarkable.
Okay, one more case study. Branch and bound.
Right. The R1 version for branch and bound. Again, it used nearest neighbor for a better initial upper bound. But crucially, it also dynamically sorted the candidate nodes to explore.
How did it sort them?
Based on the weights of the edges involved, essentially prioritizing branches that looked more promising early on.
Ah, so it could prune the search tree more effectively.
Yeah.
Lead to faster solutions.
Exactly. Faster convergence to the optimal solution. These case studies really nail down how the LLMs are adding value by applying known, effective optimization strategies.
It's not just random code changes, it's intelligent modification. Did they look at code complexity at all? Like, did the LLM code become harder to read?
They did look at that using cyclomatic complexity as a metric. It measures how many different paths there are through the code.
More paths, potentially harder to understand or debug.
Generally, yeah. Interestingly, code generated by Claude tended to have lower complexity, maybe simpler or more readable, but it wasn't always the best performing.
So a trade-off sometimes.
Sometimes. But here's a really nice finding. Some of the top performers, like R1's genetic algorithm and Christophedes and O1's Sarsa, they actually reduced complexity compared to the original code while improving performance.
Oh, that's the dream. Better and simpler code.
That's a real win-win, yeah. More efficient and potentially easier to maintain.
Okay, so stepping back, what does this mean for, people listening? What are the broader implications here?
Well, I think it paints a picture of a future where optimization becomes more accessible.
How so?
Imagine someone working in, say, logistics or manufacturing. They might have a decent routing or scheduling algorithm, but they aren't optimization gurus.
Right, they're experts in logistics, not necessarily algorithms.
Exactly. This research suggests they could potentially use an LLM, feed it their existing code, and get back an improved version tailored maybe even more to their specific needs without needing to dive deep into algorithm theory themselves.
It's like having an optimization consultant on tap.
Sort of, yeah, an AI consultant. It could really lower the barrier for people in various applied fields to leverage more powerful optimization techniques.
That could lead to real efficiencies, better delivery routes, smoother factory schedules.
Potentially significant real-world impact, yes. It also suggests possibilities for rapid prototyping, trying out different algorithmic ideas quickly by prompting an LLM.
Customizing algorithms on the fly.
It feels like a step towards democratizing these advanced computational methods, making them usable by a wider range of people.
That's genuinely exciting. Okay, great summary. Now it's time for our Novel Notions segment. This is where we brainstorm some speculative future ideas inspired by the paper.
All right, let's speculate. So the paper shows LLMs improving static code. What if we took it a step further?
Go on.
What about using LLMs for real-time adaptation? Imagine an LLM agent watching an optimization algorithm run on a specific problem instance.
Watching it live.
Yeah. And based on how it's performing, the LLM dynamically prompts itself to maybe change heuristics, tweak parameters, or even swap algorithmic components mid-run.
Whoa. So the algorithm adapts itself to the specific problem it's solving right now.
Exactly. The paper shows LLMs can pick good techniques. This idea leverages that but makes it dynamic. The LLM could analyze the problem structure as it's being solved and adjust the algorithm strategy accordingly. That
sounds incredibly powerful, like for problems where conditions change, maybe. Dynamic routing or scheduling.
Precisely. You could potentially get algorithms that are hyper-specialized to the immediate context, performing way better than any static algorithm could across diverse situations. Super adaptive optimization.
Okay, that's a cool idea. Very sci-fi, but grounded in what they showed. What else?
Here's another angle. Creating a feedback loop. We have LLMs improving algorithms now. What if we collect data on how well those LLM-improved algorithms perform on real problems?
Collect performance data. And then
use that massive data set problems, LLM suggestions, performance results, to fine-tune the LLMs themselves. Create a new generation of LLMs specifically trained on optimization success stories.
So you're not just using general-purpose LLMs, but building LLMs that are experts in optimization strategy improvement.
Exactly. Optimization-aware language models. They could learn much deeper patterns about what kinds of modifications work for which types of problems and algorithms.
They might even discover totally new ways to combine techniques, things humans haven't thought of.
That's the potential, right? It could lead to the discovery of novel algorithmic paradigms, maybe even surpassing human-designed algorithms in some areas by learning from this vast feedback loop of trial and improvement.
It's like accelerating algorithmic evolution using AI, specialized AI tools pushing the boundaries of optimization.
Could revolutionize fields that rely heavily on optimization? Think drug discovery, material science, complex system design.
Really fascinating possibilities. Okay, great stuff.
Exciting times for the field.
Definitely. And just a quick reminder to our listeners, these novel notions are purely speculative ideas, just for fun and discussion.
Food for thought.
Exactly. You can find a link to the actual paper we discussed today in the show notes. Thanks for tuning in to Talk Tensors. Join us next time for another deep dive.